All right, we are recording. Please stand. In nomine Patris, et Filii, et Spiritus Sancti. Amen. Sancta Michael Arcangelo, defende nos in predi, contra nequitiam et insidias diaboli, est oppressivi, impere Filii Deus, supplices deprecam, tuque princeps militiae celestis, Satanam, aliosque spiritus malignos, qui ad perditionem animarum pervegantur in mundo, divina virtute in infernum destruit. Amen. In nomine Patris, et Filii, et Spiritus Sancti. So please have your 1F. I don't know what happened to the 1. I suspect somebody's finger went by there. Yeah. I quoted your
Oh, that thing's long though.
what?
I put your quote when you said I quoted that on the game.
So the police are gonna pick me up.
No, it's fine. It's
Okay.
it's for weird stuff.
I'm on the FBI flag list now. All right. Again, 1F, which is on page 34-ish, 35, somewhere in there. Should be 379, basically 3 through 27, skipping a lot.
We already checked that.
Oh, we did 1F?
Yeah, I think.
I think we did both. We did both.
So and we didn't get to 1G?
No, we never did that.
We didn't have time.
So I didn't assign homework 1G.
No,
Oh, that's right, because we got within like 4 minutes at the end of the hour. My brain is just caught up with me. Thank you. With an assist. Take out your notes, please. My bad. Oh, yes. Thank you. I want to talk a bit about quadratic graphs today. And for those of you who need the answers to 1E and 1F, go on YouTube. Does anybody not have the YouTube link to the videos for this class? Okay, I can send them out again, but if anybody needs it, email me. Let me know, and I can send it to you. Okay. All right, let's talk about quadratic graphs. Now then, a quadratic, can somebody refresh my memory what that is again? What is a quadratic? Just in general. Go. Degree of 2, correct. Degree is the highest power, so it is the highest power of 2. And quadratic graphs are usually what shape? Go. Parabola. Usually a parabola. If the quadratic graph is a function, then it's almost always a parabola. If it's a polynomial function, then it's always a parabola. Anyway, we'll get more on that later. But can somebody refresh my memory for the parabola pattern for graphing? What point do you start at, first of all? The vertex. Start the vertex. And then you go what? What's the pattern for a normal parabola? Other way around, but yeah. Over 1, up 1. You do over first.
Yeah, over 1 up 1.
So over 1 up 1. What's the next one?
Over 2.
Over 2 up what? 4. Over 3 up 9. And then blah, 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 blah. What if I went over n? How do you get the next number? What was it? N squared, okay. So that's the normal parabola pattern. Over 1, up 1. Over 2, up 4. Over 3, up 9, etc. Gentlemen. So just as an example, the most basic graph of a parabola is y equals x squared. The vertex is at 0, 0. Then you go over 1 both ways and up 1. So over 1, up 1 in both directions. Then start over 2, up 4 in both directions. Then if you wanted to have a nice looking parabola, you do another pair, over 3, up 9, it'll just go off screen. Make sure it's curves on the bottom. It shouldn't come to a point, and it shouldn't be flat either. It should be a rounded point, if you will. So there's a standard parabola. Does that make sense? Now today, I want to talk about 3 different ways you can change a parabola graph, in any graph. Before we do, I want to talk input versus output of a function. Whenever you talk about a function by definition is one input yields one output. You plug one thing in, you'll get exactly one thing out, not 2 or 5, which is 1. When you're talking about input versus output, there are 3 key differences. Input is usually represented. Does anybody happen to know which letter mathematicians love to use for input? Usually what? What do you think? When you plug something in, it's usually what?
X.
It's usually x. When you have a function, it might look like this, f of x. And x is a very popular input variable. You don't have to. You could have f of t, f of w, but x is very common. What's one of the most common output ones? Please. It's usually what? Yeah, it's usually y. It doesn't have to be, but it often is. And that indicates what direction you're going to be. Input deals with, when you're doing a graph like this, which direction does the input go? Well, yeah, right, left. So in other words, left, right, or horizontal. And correspondingly, Katie, what's the output direction? Vertical, or up, down. So whatever letter they're using for the input, that's going to be the left-right axis. So somebody could play, normally this is the x-axis and this is the y-axis. Somebody could play with your mind and try a t-axis and an a-axis. There's nothing stopping it. It's weird. I'd be the first one to admit that. But you can graph using any 2 letters you want. It's just that the input is always left-right. And the output is always up-down. You can substitute whatever letter you please, but input is always left-right, output is always up-down, just so everybody gets it straight. The third, which is actually the most important difference, does anybody happen to remember how input behaves? If you've had me before, you may have heard this. Yeah. It does the opposite of what you expect. I'll explain that. It does the opposite of what you expect. What does that mean? Well, one example I use a lot is every once in a while, like, have you ever heard of something like in the bathroom? It's called a 3-way mirror, where there's people that it's kind of like 3 panels of mirror, and you can actually open the other 2 and see the back of your head, kind of, sort of, ish. So I use that to, cut some of my hair if it gets really crazy. I'll spare you the story, but all right, fine. So I used to shower right before I went to bed before I realized how horrendous I looked in the morning, because if my hair is wet and then I happen to hit the pillow like this, I've got this sort of peacock thing on the side of my head, and even, it takes a gallon of hot water to get it slicked back down, and even then, after about a half hour, it starts springing back up. So eventually I had to start taking a clippers and saying, you know what, you're just gonna take it for the team, buddy, because I can't have you doing this every day. But I needed, you ever try cutting hair in the back of your head? It's super duper challenging. So, that being said, let's just say, I'll take a smaller example. There's like this little lock of hair that just goes boing, and I want to say, all right, I need to just clip this off because it's just not behaving itself. Trying to cut your own hair with the scissors in the mirror is downright dangerous, because you know why? What happens when you're trying to move around? Yeah, everything's backwards. It's like I'm moving up and down, and I've stabbed myself 2 or 3 times with the scissors. It's awkward. But everything is reversed. One last example on that. That was sort of a true story, by the way. It's a true story compiled over years. But when you stand in front of the mirror, and I know everybody does this, but if you stand in front of the mirror and like wave at yourself, I know it's a popular thing to do. If you're waving with your right hand, what's your mirror image waving with? It's left hand. The imaginary you in the mirror is waving opposite. Everything's reversed. If you have like God forbid, a black eye on your right eye, your mirror image is going to have a black eye in the left eye. Everything's reversed. If you pretend that that's another you inside the mirror can be thought of as input. Inside the mirror, everything's reversed. Left is right and right is left. Outside the mirror, everything kind of behaves itself. So the third thing for output, it does what you expect. I'll explain what that means mathematically in a second. It does what you expect. Input does the opposite of what you expect. Think being inside the mirror and reversed. And then output does what you expect. It's like being outside the mirror and everything actually. You hold up your right hand and it's your right hand. Make sense? That's true everywhere. It's not just in pre-calc, it's in all levels of math whatsoever. Does everybody have this first part with the parabola back? I'm trying to write small to keep it on screen here. So we'll see how good of a job I do. Once you have this table, I'm going to give you one more table to show that there are 3, arguably 4, ways to change any graph. Physically speaking, let's say if you have a graph of a parabola, there are really only 4 ways you can change a graph standardly. There are weird ways like it is in here. You could paint a parabola on a sheet of rubber and then like poke a finger underneath it and get all sorts of weird shapes. But I'm not talking about that yet. We're assuming it's still on a flat sheet of paper. 3 ways to change a graph. I'll give you a 4th one, but we're probably not going to cover that till 2nd semester. The 4th one is going to be extra for now. First, you can move it. You can take the parabola and move it up, down, left, or right, or some combination. You can move a graph anywhere. The second thing you can do is resize. You can make it bigger or smaller. Now there are 2 ways to do that. You can do it bigger or smaller in the up-down direction, which is taller and shorter, or you can do it in the left-right direction, which is wider or narrower. So there are 2 different ways to resize and 2 different ways to move. So you can move up, down, move left, right. You can resize up, down, and resize left, right. The third thing is flip. And there are 2 ways to flip a graph. You can flip it upside down, or you can flip it backwards, left, right. The 4th, again, which we're not going to cover much until the 2nd semester, you can rotate the graph. Now, if you continue on to take math in college, you might cover I'll give you a little teaser. It is possible, like a rotation, like you grab your paper and rotate 30 degrees clockwise. It is possible any rotation can be done with some weird combination of moves, recesses, and flips. You don't absolutely need rotation. You can do it with a combination of the top three. It can be hard. It's usually way easier to just say rotate at 30 degrees clockwise than to try and find all the really creative moves, recesses, and flips. How do you rotate something? Does anybody remember their trig from last year? Trigonometry? Sine, cosine, tangent?
Oh, yeah.
Okay. This year, we're going to, does anybody remember playing with matrices last year? If you were in my class, you did. We added matrices, subtracted, multiplied, divided. In order to rotate something, you have to multiply by a particular matrix that has 4 trig functions. We'll talk about that later. But it's a little involved. But it is possible. By the way, if anybody wants to go work for Pixar, you'll need to become familiar with that. Either that, unless you want to just sweep the floors at Pixar, in which case you don't have to. So, what does all this mean for graphing? Well, I'm going to have you tell me. Watch this. Quick example. Y equals x squared versus y equals x squared plus 3. Go ahead and write that down. What's the difference? Like if you graph those, can you tell? Obviously, they'd be a little different. They're very similar. They both have y equals x squared. So I'll say right now, they're both going to be parabolas. And they're both going to be very similar. But there's going to be at least one thing different. I'd like to know what. Quick down.
Is the vertex going to go up?
Yes. This, and I'll explain why in a second, this moves the graph up 3 spaces. One way to find out is actually to graph that. We're not going to, but if you have, it's really pretty slick if you have a computer or a graphing calculator. Don't need one this year, by the way, and they're expensive. But you can get like free graphing programs on a calculator or a computer and just poke. I'm sure that's exactly what everybody does on a Saturday night. I know. Okay, I do sometimes. But you can they're free. You can download them, make sure they don't have viruses or anything on them. And then plug in this. There's some things that even do it online. You don't have to download it. Plug this in and then plug this in and watch what happens. It looks like this. Y equals x squared looks like this. Y equals x squared plus 3 looks like this. It's the exact same shape, only moved up 3 spaces. So you can try it on your own or just take it on faith, but it is true. Question, why did it move up? There are 4 possible places it could have moved. Could have moved up 3, down 3, left 3, right 3. Can somebody tell me why it did not move down 3? Yeah. No. Positive. Positive is associated with 2 directions. Mary, can you name them? Just on a graph, what would you normally associate with positive? What directions? Up and to the right, correct. So if it's plus 3, I'm expecting to go up, and I'm expecting to go to the right. Does that make sense? So I'm not expecting it to go to the left, and I'm not expecting it to go down. Why not to the right? This is a little more obscure. Does anyone know? Yeah.
Because it's not with the input.
Yeah, everybody take a look up here. I'd like you to insert one thing into what you wrote. Put parentheses around the input. So it'll look like parentheses x squared plus 3. The reason I do that is to make it look like a function. The stuff inside is the input. The squared is the actual function itself. And anything outside the squared is output. I'll give you a clearer example of that in a second. Like for example, let's say f of x is equal to 2 parentheses x minus 3 parentheses squared plus 4. Can anybody tell me what shape that's going to be? Let me see. Hey, what shape is this going to be if I graph it? Parabola. What told you that? Squared. The fact that it's a squared, this is the function itself. The fact that it's squared. Now the question is anything inside the square and is anything outside the square? I would propose that this and this are outside the square, which means we call it output. Anything outside the main function is output. And anything inside the square, by the square I mean this, is input. The minus 3 is in the input. The x is in the input. The times 2 and the add 4 are in the output. That's why I do the parentheses here. The plus 3 up here is not in the input, otherwise it would be squared. So it must be output. Look at our chart. Input versus output. If it's output, it's going to change vertically. There are only two options for this. It could go up 3 or down 3. If it's output, up 3 or down 3, that's it. Does that make sense? If it were input like this, the minus 3, there are only two options. To the left 3 or to the right 3. Input is always horizontal. Always. So anytime you're doing anything in the input, adding, subtracting, multiplying, dividing, whatever, you're changing the input. You're changing the graph left, right. Anytime you change outside the square, you're changing the output. You're changing the graph up and down somehow. Either moving it or resizing it or flipping it up or down. Make sense? So if you can recognize in a formula what's input and what's output, half the battle is done. Let's try a few of these. Is that where I can? This, I think I'm going to get rid of this stuff. Well, darn it. I have these three big beautiful things and they're off screen. So I'm just going to do the 3 ways to change. You don't have to write this again. Because I need to point to it. 3 ways to change any graph. Well, move. Sorry, that was sloppy. Move. Resize. Flip. And later on, we'll talk about rotation. Rotate. Okay. Let me give you another. I'll do y equals this time. I want to compare this with y equals x squared. How is it different? Becca, if you'd be so kind, name me one difference comparing this to this. Just visually, what do you see first?
There's parentheses in the first one.
Okay. And what purpose did this serve? That's the input. Is there anything in there? Like what? And a -1. I want to know what that's doing. First of all, can somebody tell me, is that moving, resizing, or flipping something? Jeff?
Which one?
The -1.
It's moving.
It's moving. Why do you say that?
Because it's.
This is from last year. I'm going to fill it in here. So when you still have your chart with the move, resize, flip, be ready to plug. I'm going to just a teeny weeny little bit of writing out of here. What two math operations move things. Addition and subtraction. When you add or subtract anything, it moves the graph. Can somebody hazard a guess as to what would resize a graph? Well, yeah, multiplication and division. You can make it bigger or smaller. Can anybody hazard a guess as to what would flip a graph? Courtney. How would you flip a graph upside down, for example? What would you think would be a way to do that? Right, I mean, what do you do with the formula? What do you want to say? What kind of parabolas go down? Got it. Switch the sign. Make it negative. Or if it's already negative, make it positive. When you flip a graph upside down, you're making part of it negative. Does everybody see why this is a move now? Because it's subtraction. Any addition or subtraction is a move. So, Josh, this is a move. Is it input or output? Input. Because it's inside the square. Rainy, if it's input, what direction does that go? Left, right, or up, down? If it's input, it goes left, right. Can anybody tell me which one? It's going to move one space, but is it going to move to the left, or is it going to move to the right? And I'll warn you, there's something a little bit tricky.
To the right.
Why do you say to the right?
That's opposite.
Ah, sneaky. Take a look up here. -1 in the input, minus is negative. We normally expect negative go to the left. I mean, if you're doing left, right, negative is to the left. This is actually going to move it to the right. Moves to the right one space. And the reason is what again?
That's the opposite of what you expected.
It does the opposite of what you expect. This is where the input opposite of what you expect actually makes a difference. If you subtract from the input, you'd expect it to go to the left one. It doesn't. It goes to the right one. Input always does the opposite of what you expect. So this means it moves to the right one space. Austin, what does this thing do?
It's gonna move the.
First of all, I'm sorry, I should say it again. Move, resize, or flip.
No, move.
It's a move. Explain.
It's gonna move. Well, wait, it's gonna move up because it's addition.
It's addition. And then is it going to be input or output?
Output.
Output. Because it's outside the square. What direction does output go?
Up, down.
Up, down. Can you tell me if this is going to go up 5 or down 5?
Up, 5.
Why do you say up 5?
It's positive.
Yeah, it's positive. Does it do what you expect?
Yes.
Yes. Output insists that you be either 5 up or 5 down. And the fact that it's output means that it does what you expect. Positive goes up, negative goes down, just like what we expect. Can somebody tell me what this thing is doing? Sam. Is it a move, resize, or flip? Resize. What do you say then? Yeah. Any multiply or divide is a resize. It's going to make things bigger or smaller. Is that input or output? It's output. It's outside the square. And output is always up or down. So there are two options here. To resize it in the output means to make it taller or to make it shorter. In this case, it'll either be 3 times taller or 3 times shorter. Which one is it? Courtney. Taller. Why do you say that? Right. It's output, so it does what you expect. So when you multiply something by 3, you expect to get 3 times bigger. And that's exactly what it does. As a little caution, if I multiplied the input by 3, remember input is left, right, you'd expect it to get 3 times wider. It doesn't. It's 3 times narrower. because it always does the opposite we expect. Does that make sense? Let's try this in real life. Let's try and graph this thing. Is everybody okay with this chart with the input and output? I need to get some space here. Let's actually graph this thing that I have up here. The 3 parentheses, blah, 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 blah. So graph y equals 3 parentheses x minus 1 parentheses squared plus 5. Now you remember, but this is a parabola, yes? What's the pattern for a parabola again, Katie? Over 1 up 1? Over 2 up 4, etc. Over n up n squared. Over 10 up 100, etc. Can somebody tell me where a parabola normally starts if you don't mess with it at all? Just a plain old y equals x squared parabola. Go. It starts at 0, 0. Unless they move it, it starts at 0, 0. That's the normal starting spot for any parabola, of any graph at all. Did they move it? All right. They moved it up 5. Anywhere else? Say again? And to the right 1. You have a new starting point. The starting point is no longer 0, 0. It's 1, 5. What is that starting point called again? Yeah, the vertex. The vertex, which used to be 0, 0, in this case is 1, 5. Can somebody tell me how to graph the parabola? Josh, how do you graph this parabola? What's the pattern? Normally it's what? Over 1, up 1, over 2, up 4. What's different about this one? Look at the stuff we have over there. Yes, the parabola is 3 times taller. So instead of doing the over 1, up 1, which normally is over 1, up 1, over 2, up 4, over 3, up 9, this is different. It's not over 1, up 1 anymore. It's over 1, up 3. 3 times taller. It's no longer over 2, up 4. It's over 2, up 12. And so on. It's not 3, 9, it's 3, 27. I'm not going to do all those because it goes through the ceiling. But I'd like to do at least one jump. Over 1, up 3. Over 1 the other way, up 3. And that is a reasonable approximation of your graph. Does that make sense? If you wanted to make a really good graph, make sure you have a big piece of paper. Go up 12 spaces. Questions? On the test, I'll try and make sure you can actually keep it on the screen. Usually it's a 10 by 10. From negative 10 to 10, negative 10 to 10. I'll give you graphing paper on the test. Everybody feeling okay there? Think that makes sense? All right. Now, let me see if the book did anything funny. There are a few objects which you'll need to find. First of all, any questions before I erase this stuff on the line? Okay. Let's try our best. There are 4 forms of a quadratic function. A parabola function. I usually call that parabolic. That's the adjective form of parabola. There are just as there are 4 forms of a line, there are actually more than that, but 4 basic ones. There are also 4 basic forms of a quadratic. What's a relatively common form we use for quadratics? It's relatively nice for graphing. Yeah.
ax squared plus bx plus b.
That's the second one. That's called standard form. Glad you knew that. Standard form looks like this. Y equals ax squared plus bx plus c. We use that when we're completing the square. We use that when we're solving with the quadratic formula. The first one is called the vertex form. And it looks like, does that mean I remember off the top of your head? Starts with y equals, go.
So y equals a parentheses
Yes.
x minus h
Parentheses
squared plus
k. Correct. A parentheses x minus h, close parentheses, squared plus k. Where in that case, the vertex, sorry, I'm cramping this, is h comma k. Let me get rid of this other stuff so you can see a little better. Sorry, I'll add it in just a second. So in vertex form, it gives you the vertex on a silver platter. H comma k is the vertex. Keep in mind there's a minus here. It's not x plus h, it's x minus h. I'll explain that in a moment too. The third, which is a little more obscure, it's called x-intercept form. So we're going to write this down. It's less likely that you'll have had this in previous classes. We touched on it in second year algebra. Y equals a parentheses x minus x1, then another parentheses x minus x2. Where x1 and x2 are x-intercepts, also known as roots, also known as solutions, also known as zeros of the function. The fourth, which is very rare, is called sum product form. And I'll tell you right now, this is an extra credit potential on the test, if you know this. Sum product form, we'll eventually use it for real, but this time it's a good extra credit opportunity. Y equals a, parentheses, x squared minus little parentheses, sum times x plus product. X squared minus sum times x plus product, with the a way, way, way in front, multiplying everything. Again, a is the height multiplier for every single one of these. Sum is basically the two x-intercepts added. It's x1 plus x2. And the product, so you can probably guess, is the answer to the multiplier for its x1 times x2. It's an obscure form. It comes in very, very handy sometimes, especially when we do complex roots. I've run into, for example, this. I think we have time for this. Example. I'm going to say, what on earth would you ever use this for? If a quadratic function has solutions, x equals 2 plus 3i, and x equals 2 minus 3i. And a height multiplier of 6, find its equation. find the original equation that would have two solutions, 2 plus 3i and 2 minus 3i. That seems like a monster chore. There are many ways to do it. Most of them are long and painful. The one I'm going to show you is medium and minimally painful. Can somebody tell me the sum of those two roots? It's a lot easier than you think. Go. 4. How do you get 4 so fast?
You just subtract, add them, and then the 3i cancel out.
Yeah, 2 plus 3i, 2 minus, what am I doing? 3i, cancel, the sum is 4. Interesting. Can somebody give me the product? 2 plus 3i times 2 minus 3i. Suggestions? How do you do that? We've actually been doing this for the last week. Hey, help me out. What? FOIL, go for it. Minus 6i, plus 6i, minus 9i squared. Is anything simple about it? 6i's cancel. What's I squared? So what's negative 9 times negative 1? What's the final answer? 13. Anybody think they give you the equation? The height multiplier is a, by the way. Becca, try this. Use, which formula do you think would be best? First, second, third, or fourth? Fourth. So y equals what? 6. Parentheses what? There's no value of x, so just leave it. X squared. Minus, and parentheses is optional at this point, but 4x plus, we're done. I guarantee you, if you solve that with the quadratic formula, you get x equals 2 plus 3i, x equals 2 minus 3i. We can do it tomorrow if you want. Questions? So you can reconstruct some pretty complicated quadratics just by knowing the 4 forms. Again, the 4th form is not going to be required yet. I'd like you to know the first 3. The first 3 are quite useful. What I would like you to do, take out your book, please. I want to walk through the next homework, which is 1 G's and goats, I think. And I realize this class feels like I'm kind of being a slacker here. This homework is not due tomorrow, it's going to be due Wednesday. But I would like you to start on it. Pretty much it says sketch each parabola, and it has a bunch of terminology. I'll tell you what they mean. For example, number 1. I need to erase something. Which, yeah, page 41. Good question. Does everybody have the 4 forms? Anybody still need that? Speak now for all duties. People at home, you can just rewind. Couple things. Let's assume this is, whoops, no. I got a blue thumb, that's great. Go ahead and sketch that. It's a parabola with a point. It hits the y-axis at 15. It hits the x-axis at 3, and then again at 7. what are the names of those special points? I mean, what are these called? X-intercepts. What's another name for x-intercepts? Yeah. Solution, roots, etc. Forgot what, oh, whatever. The x-intercepts are x equals 3, x equals 7. Those are also solutions. Any other special points anybody see there? Name. What's that? What is 15? Y-intercept. Y equals 15. I would also point out that the x-intercept is 3 comma 0 and 7 comma 0. And that the y-intercept is 0 comma 15. X-intercepts always have a 0 at the end. Y-intercepts always have a 0 at the beginning. Clear? Can anybody spot a point I have not identified yet? Go. The vertex. Can anybody tell me anything at all about the location of that vertex? So the vertex is h comma k, but you should be able to give me one of those two numbers. Yeah. I'm sorry? Definitely quadrant 4. 1, 2, 3, 4. One of those two numbers you should be able to specify. Just given the data up on the board. Anybody think this is it? Yeah.
Yeah, is it, it's the median, or it's the, yeah, it's the average of the 3 and 7.
Yeah, so what's halfway between 3 and 7? 5. I don't know how low down it is, but the first one has got to be 5, because it's exactly halfway between. By the way, I just drew a line that has a special name. Can anybody identify it? Go. It's a what? An asymptote is where it swerves and never touches. I like the first syllable. Yeah. That's yeah, it's called the axis of symmetry. It goes right through the vertex. In this case, x equals 5. What they're going to do in the homework is they're going to ask, here's a graph. Here's a graph. Find the vertex. Find the axis of symmetry. Find the x and y intercepts. Then sketch a graph. Make sense? How do you find the x intercepts? We covered this the other day. What's another name for x intercepts? Megan. Another name for x intercept. They're like 4 names. Give me one. Okay, an x-intercept is also called the root. It's also called the 0 of the function. It's also called a, starting with an S. SO. This is going to give it away. SOL. Solution, nice. These are solutions. That means that when you solve the quadratic, you'll get x equals 3 and x equals 7. If they give you a formula, set it equal to 0 and solve it, you'll get your 2 x-intercepts. Can anybody tell me how to get the y-intercept? Like if I give you this, y equals x squared plus 5x plus 7. Can somebody give me the y-intercept? It's actually very fast. Austin, what do you think? What is a y-intercept? What's that?
It'd be like 7.
It's 7. How do you get that so fast?
Just do 0, use the 0 for x.
Yeah, y-intercept, remember, as a 0 for x. 0 comma something. Watch what happens when you do that. 0 squared plus 5 times 0 is 0 plus 0 plus 7. So to get an x-intercept, solve. Set it equal to 0 and solve. To get a y-intercept, just plug in 0, which is usually easier. To get the axis of symmetry, go halfway between the solutions. That'll at least give you the first, x equals whatever. To find the vertex, there's one last thing. You already have a number. It's the axis. In order to get this, plug in to the equation. And find why. That's the last thing I need to tell you today. So again, for tomorrow, what I'd like you to do is look over the homework on page 41. If you have your homework guide sheet, page 43. Actually, no, 37. Page 37 is where the reading starts. You're going to be doing 1A, 3, 7, 11, 15, and 27. So I would say look ahead to those, and if you can solve any of those, do it. It'll be less work for you to do tomorrow night. And you'll also be able to bring questions. Questions? No pun intended. Alrighty. So go ahead and let your brains cool off for a minute or two. See. Yep.
See, it was 1.2. Yeah, that's not right.
Oh, heavens. Thank you. Wow.
I forgot how that applies
Anyway, for those of you listening at home, thank you for your patience. Sorry, that made it a little long. This is my hand waving goodbye. Talk to you later.